Hello, my name is Nicholas Svoma, and this is my presentation of a technical article for power system operations with renewable energies. The technical article I chose to research is on operational optimization and demand response of hybrid renewable energy systems. The paper I will be discussing was researched by two professors and a researcher from the Department of Chemical Engineering and Materials Science at UC Davis. It was published in February of 2015. The paper reviews a hybrid renewable energy system model design approach which they had developed. The strategies reviewed include both generation and demand sides of energy management. The optimization approach, receding horizon optimization, which I will discuss later, was chosen for its increased reliability. To further increase system efficiency, real-time prediction, optimization, and demand response are included in the model. This study applies a hybrid renewable energy system to a single residential home and discusses the benefits of expanding the system to multiple homes in a given area. I chose this paper because of my interest in the modern problem we are facing of an increasing demand for energy in combination with calls for reduced carbon emissions to combat climate change. Current methods of generating and delivering energy cannot address both of these needs simultaneously, leading to a need for restructuring our energy infrastructure. Hybrid renewable energy systems are a feasible method of beginning to address this problem. Eventually, it is desired to transition to a fully renewable energy system, but a good first step in that direction is a hybrid system. This study provides a comprehensive look into how a hybrid renewable energy system can provide the energy needed, when it is needed, for a typical residential home while greatly reducing reliance on fossil fuels. Renewable resources used for generating electricity are intermittent, which demands a need for multiple sources in order to have both stability and reliability. Let's look at what energy generating machines are included in the hybrid renewable energy system researched in this paper. First is the solar energy conversion system. This system is a typical solar energy system using photovoltaic panels to convert sunlight into electricity. It uses an inverter to convert the direct current electricity generated by the panels into alternating current electricity that is usable by typical household appliances. To determine the contribution of electricity from the PV system to the hybrid system, performance models provided by the manufacturer are used to get the current voltage graph seen on the right, as well as the maximum power point, which will keep the system operating in an optimal state. Also, to determine the steady state performance of a module, the equations shown are applied. The main cost of the solar energy system is in its initial parts and installation, with some cost in maintenance. No fuel costs are required. Wind energy is also a viable renewable energy source for a hybrid renewable energy system. The power output contribution of a wind turbine to the total power of the hybrid system can be calculated using the equation shown. Below that is the typical curve of the relationship between the turbine's power output and wind speed. When the wind speed is less than the cut-in speed, no power is generated. Between the cut-in speed and the rated wind speed, the wind turbine output power is directly proportional to the third power of the wind speed as shown in the equation. When the wind speed is greater than the rated value, the output power needs to be limited to prevent damage to the generator. If the wind speed is higher than the cut-out speed, the system will be stopped in order to protect it. The main cost of the wind energy system is its initial parts and installation, with some cost in maintenance. No fuel costs are needed. A diesel generator is included in the system to increase reliability by supplying energy not met by the renewable generation, or by charging the backup battery system. The power contribution of the generator to the total power of the hybrid system can be calculated from the equation shown. The main cost of the generator is in fuel consumption. A battery storage system is included in the hybrid system to store excess electricity produced by the renewable generation systems. In this case, deep cycle lead-acid batteries are chosen for their low cost and high reliability, regardless of their smaller storage capacity. For sizing purposes, the battery capacity can be calculated using the equation shown. In order to optimize the battery system performance, the state of charge of the battery system must be estimated and kept at a certain level in order to increase battery longevity. The main cost of the battery storage system is in initial parts and installation. Sizing each part of a hybrid renewable energy system correctly is key in ensuring the most electricity will be generated at a location at the lowest possible economic cost. The annual average hourly energy consumption data of a normal-sized family in Northern California on a typical day is used as the reference demand. Two types of optimization approaches are demonstrated. The first approach is referred to as iterative optimization, and it uses the total energy generated from wind and solar to balance the total demand, while variations in the demand profile are offset by other sources such as the generator or battery storage. While this approach does provide the optimal combination of components to minimize the overall economic cost, it does not consider any operation cost of electricity generation and transmission. The procedure for this approach is: first, select commercially available wind turbines, PV panels, and battery storage units. Next, fix the number of wind turbines and increase the number of PV panels until the energy is balanced. After that, repeat the previous step for different numbers of wind turbines to achieve all available combinations. Finally, calculate their required storage capacity by summing up all variations of energy between the PV and wind supply and the storage. The second approach, which is referred to as energy flow optimization, takes into account both capital and operating costs. Using averaged weather data, corresponding upper limits of solar and wind energy generation can be determined. Capital and operating costs are determined as a daily cost and added together to get the economic value that needs to be minimized. Systems are sized to match peak demand, so lowering peak demand is able to reduce the overall cost. In addition to sizing multiple generating units to meet demand, another important approach to improve the overall system reliability is to use receding horizon optimization. To optimally allocate generation among the available generating units, an accurate prediction of available solar and wind energy is necessary. The variables that decide the availability of this energy are solar radiation, wind speed, and ambient temperature. Online forecasting is used on brief time scales, such as 15 minutes or an hour, in order to update the available energy generation frequently. Real-time weather data can be obtained from statistical or physical approaches. In a receding horizon strategy, a certain cost function is minimized over a moving time horizon to determine the optimal power references for the various energy generation systems. The figure seen to the right demonstrates the receding horizon optimization graphically. The x-axis represents time divided into predetermined samples. The y-axis represents the cost of generation. As time moves forward, new weather data in combination with a past trajectory is used to create the real-time optimal series, which contains points for the optimal cost of generation within that time period. The reference trajectory, is created using a predictive model over a number of days to determine what the cost of generation is predicted to be during any period of time. The cost function used in this model is shown below as the sum of operating and environmental costs after they've been multiplied by a weighing factor. The optimal generation targets for each unit in the generation system are shown in the graphs. The graph on the left shows the results from real-time optimization, where only information of the current time is utilized to generate the optimal strategies. The graph on the right uses a 12-hour receding horizon to create the generation capacities. The differences are subtle, but they have significant economic consequences. The table below provides operational data in terms of varying receding horizon times. It can be seen that the longer the horizon time, the lower the operating cost at the expense of computational time. It was determined in the study that a 12-hour receding horizon provided the best trade-off between cost and computational time. It is rarely possible or desirable to change the output of renewable energy sources to follow a particular load shape. Therefore, in a hybrid renewable energy system, the load demand is expected to take more of an active role to match the electricity generation. A demand response strategy is explored in two stages: day-ahead scheduling and real-time dispatch and adjustment. In the case of this study, the electricity producers are assumed to be the same as the consumers. A preliminary estimation of the electricity consumption for the coming day is made by the household. Weather data and time period factors are included in this estimation. Flexible loads such as dishwashers, washing machines, and clothes dryers are arranged to be used at a certain time, typically late morning, in order to better match the renewable generation. A consumer's willingness to shift their demand is represented in a cost factor, which goes up as time goes on if the consumer is less willing, or down if the consumer follows the demand response. The optimization of this situation needs to achieve a desired trade-off between minimizing the electricity cost and minimizing the waiting time for using each appliance. The demand profile for a single day before and after responsive shifting is shown in the graph to the right. In conclusion, the receding horizon strategy is shown to be able to optimize the cost of generation for a hybrid renewable energy system over a given time period. In applying this approach, users can also gather information about future conditions in order to make rational decisions about their energy management. Compared with the traditional methods of operation for energy systems, using the combination of real-time prediction, receding horizon optimization, and demand-responsive methods is expected to improve the overall system efficiency and better utilize the available resources. Further investigation into more detailed combinations of demand-side and generation-side management strategies, as well as considering connecting the system to the electrical smart grid in order to scale to larger applications, would be beneficial to the effective implementation of a hybrid renewable energy system.